Hey everyone, welcome to my channel. So, in my experience as a math tutor, I've gotten a lot of questions about calculus, so I decided I'm going to start my first few videos with calculus and then I'll move on to other levels of math later on. So, what I'm going to start with first is I'm going to start off with an introduction to limits. So I'm just going to, in this video, introduce the idea of limits, and then in another video I'm going to show you some of the kind of interesting properties of limits. So let's get started. Alright, so for this first graph I have here, this is the graph y equals x squared. And one thing you might notice about it, well, of course, is that as x is getting closer and closer to 0, y is also getting closer and closer to 0. And this is going to be important because this is what's going to establish the idea of a limit. The idea that as x is approaching a certain number, y will also be approaching a certain number as well. Alright, so in our first example we have the function f of x equals x plus 2. And below it I have a table of values going from 2 to 4. But the thing about it is that I don't have what the value for x equals 3. And the reason for that is because I'm going to find the limit as x approaches 3 using a table. So, given this table, we have values for x that are getting closer and closer to 3, going from 2 to 2.5, as close as we can get to 3. And then one thing you may notice is that as x is getting closer to 3, f of x is getting closer to 5, which makes sense because if we plug in 3 to our function, we get 3 plus 2, which is 5. And I can illustrate this further with a graph, which also demonstrates the same thing. So here we have the graph of f of x equals x plus 2, and I use these dotted lines to show that as x is getting closer to 3, f of x is definitely getting closer to 5. And then there's one last way I can demonstrate this, and that is using an more algebraic method. And this is where I introduce you to the notation of limits. Right. So if we want to write this in limit notation, we would write lim underneath it as x approaches 3. Sorry for my really bad arrow here. Of our function x plus 2. And in cases like this, sometimes what we can do is we can just plug in x directly. And when we do that here, that gives us 3 plus 2, which is 5. So here, we have shown 3 different methods to show that f of x, the limit as x approaches 3 of x plus 2 equals 5. It's not always this simple though. And I have a couple examples that will show what I mean by that. Right. Oh yeah, and also before I forget, just in general for any limit that you do, this is how it would be written. The limit as x approaches c, where c is a constant, of f of x, so whatever your function is, equals L, which is the answer for your limit. So this is just kind of like the general form of limit notation. So now on to those 2 examples that I was talking about earlier. So the first one is a piecewise function. So we've got f of x equals x squared plus x minus 6 when x is greater than 2. Oh, sorry, less than 2. Oops. Less than 2. And then it is x minus 2 when x is greater than 2. Almost messed up again. And then it's x when x equals 2. So in this particular example, what we would know is that if we were to take the limit of f of x as x approaches 2, then if we were to plug in 2, we'd get 2, but if we had the graph, what we would notice is that this is actually not the limit, because the limit is actually not something that is based on what f of 2 or f of c, using the general form, is. In this case, well, this is a case where the limit is actually different from the value that is defined at 2. Because if we were to look at when x is greater than 2 and when x is less than 2, well, let's plug 2 into those and see what happens. So when x is less than 2, then what we have is the limit as x approaches 2 of x squared plus x minus 6. And if we plug that in, we get that would be 0. And as we all know, 0 is definitely not 2. So that's just one of the cases. And so basically from the left side of this function, the limit is 0. So what happens if we plug in the other one, where x is greater than 2? Then we have the limit as x approaches 2 of x minus 2, and then that is also 0. Which means that as x is getting closer and closer to 2, without equaling exactly 2, it's actually getting closer and closer to 0, even though f of 2 is 2. So that's just one example. And my next example is just one where f of x, or I guess f of c, doesn't exist at all. So my next example, f of x equals x squared minus 1 over x minus 1. Alright. So one thing you may be thinking is that we could simplify this. And if we did that, we would have just x plus 1, and well, if we did that, then it would be defined on all real numbers, problem is, this function is not defined on all real numbers. Although this does have a limit, it does not actually have a defined value at 1. So let's take the limit at 1 and see what happens. So the limit as x approaches 1 of x squared minus 1 over x minus 1. And for this, we can't really plug in 1 here, because if we did that, then we would just get 0 over 0. But what we can do is what we did up here. We can simplify it. Alright. So this is how we would find the limit when x doesn't exist, but it still might actually have a limit. And then I'll cover some more examples like this later, but ultimately what the takeaway I hope you get from this video is that sometimes it might require some sort of simplifying, as well as some trial and error as well. But that's just kind of how limits are. And the reason why I decided to start with limits, and why really any calculus class would start with limits, is because after this, we're gonna deal with limits a lot more, and it's gonna be like one of the fundamental concepts of calculus. So, until next time.